Hello everybody, my name is Sunil Shetty. I'm from National Institute of Technology, Karnataka, Surathkal, and from the second year of the Electronics and Communication Engineering branch. Today I'm going to present on the topic spectral subtraction for noise reduction. And noise reduction is an essential topic in signal processing, especially in speech and audio applications. Today, I'll walk you through the principles, mathematical foundations, implementation steps, etc., and also the real world applications of spectral subtraction. Here's a roadmap of today's presentation. First, I'll introduce you to the reduction to the sorry. First, I'll introduce you to noise reduction and why it's important. Then we'll understand the principles of spectral subtraction, and then the mathematical formulation behind the method. After that, I'll explain implementation steps and enhancement techniques. Then we'll explore advanced variations, and finally, we'll discuss the applications and future conclusions of this matter. So the introduction to noise reduction. Noise reduction is the process of removing unwanted noise from a signal while preserving the useful information. In audio and speech processing, we in audio and speech processing, noise can come from many places, such as background chatter, traffic, wind, electronic interference, etc. The goal is simple: improve clarity and intelligibility of original audio. Here, we can highlight the three important aspects. First is signal processing fundamentals. Noise reduction often in the frequency domain, often done works in the frequency domain as it allows separate useful signal components. Sorry, it helps in separating useful signal components from noise more effectively. Next is challenges in noise reduction. It may be stationary like fan noise or non-stationary like crowd noise. And the final one is importance of noise reduction, as it increases speech intelligibility, enhances speech recognition systems, and improves communication quality in phones and hearing aids. There are different approaches to addressing noise, such as spatial filtering, which employs multiple microphones to isolate and reduce noise from other sources. Then there's temporal filtering, which works in the time domain and is effective when noise is stationary. And then we have today's topic, which is spectral subtraction, which works in the frequency domain. It estimates the noise and subtracts it from the noisy signal spectrum. They're especially effective for stationary background noises. Now let's move on to the core topic, which is spectral subtractions. This method assumes that noise and clean speech combine additively in the frequency domain. There are three main steps in this basic concept. Noise elimination. We estimate the noise spectrum during silent or non-speech segments. And then we have the spectral subtraction, where we subtract the estimated noise spectrum from the noisy signal spectrum to enhance the clean signal. And then we have something known as signal reconstruction, where we can reconstruct the enhanced time domain signal from the modified spectrum using inverse Fourier transform. The key idea is noisy signals are made up of two things, which are clean signal and noise. So if we estimate the noise correctly, we can subtract it to recover clean speech. Now we have the mathematical formulation, which is y of k is equal to x of k and plus n of k, which in the frequency domain is written as y omega is equal to x of omega plus n of omega, where where it's given, where we have x of k or x of omega as the input noise, or the input signal, and n of k is the noise signal, and y of k is the total noise and total noisy signal. We estimate the magnitude spectrum as x of k is equal to y of k x of k, x of omega mod is equal to mod of y of omega minus e of mod n omega, where e and omega denotes the expected value of noise spectrum. And in the last phase, we have something known as phase preservation, which is very important as after the spectral subtraction, it may cause phase distortion, which can degrade the speech quality. And so we preserve the previous signal in case such things happen. So reconstruction uses enhanced signal, which is equal to modified magnitude plus original phase. Now we have the assumptions and limitations. This method works under certain assumptions, which is first that the noise is stationary. It assumes that noise does not change rapidly over time and has very little to no variations. Second is signal and noise independency. Here we assume that the signal and noise are not related to each other, and which simplifies spectral elimination and subtraction. The key limitation in this process is musical noise. This can be caused by spectral subtraction, resulting in random isolated peaks, which enhance in the enhanced signal spectrum, which can be removed using mitigation techniques. Next, we have the implementation of spectral subtraction, which will be shown next. The steps for implementation is first, frame blocking and windowing. We divide the signal into frames because speech is short-term and stationary. The input signal is broken down into short time spectral intervals, which reduces spectral leakage and overlap and improves reconstruction. Then we have the noise spectrum in estimation, where we calculate the average noise spectrum during non-speech activities and commonly use averaging over multiple frames representing the noise floor. Then we convert each frame into the frequency domain using the discrete Fourier transformer to analyze the spectral components of the same signal and noise. And finally, we subtract the estimated noise spectrum from each noisy frame. We have certain enhancement techniques to improve the result, which are averaging methods, which reduce variability in noise estimation by averaging each component. Next, we have over subtraction factor, which subtracts slightly more than estimated to ensure better suppression. And finally, spectral flooring, which sets a lower bound to avoid negative or extremely small spectral values, which help reduce musical noise. Common artifacts and solutions. One common artifact is musical noise. To reduce it, we smooth the spectrum by editing the random peaks in the spectrum of the enhanced signal by smooth. And signal distortion is another issue which can happen if we subtract too aggressively. So we have to be very careful in adjusting these over subtraction factors and flooring thresholds. Then we have residual noise reduction, as residual noise can remain even after spectral subtraction, which can be negated with other filtering methods. Now let's look at improvements to basic spectral subtraction using advanced techniques and mediations. The first thing we will see is something known as adaptive spectral subtraction. Here, noise estimation is updated continuously for time-varying noises. Signal process, oh, sorry. So I will, yeah. Signal process probability, which uses signal presence probability to optimally adjust the amount of subtraction and noise unnecessary processing when the signal target is absent. And then the final one is adaptive filtering techniques like Wiener filters are used to improve noise reduction adaptively, which allows continuous adjustments and improving performance. Now we'll see something known as the multi-band spectral subtraction, where the frequency spectrum is divided into multiple bands. As the spectral subtraction is applied to each band separately, which enhances overall perceived quality and reduces artifact. This improves speech quality and reduces artifacts. As sorry. And then dependent parameters optimizes subtraction parameters for each frequency band on noise characteristics and signal properties, which allow better tailored noise reduction. Now we have integration with other methods, which is spectral subtraction can be combined with various approaches, such as the hybrid approach, where we combine spectral subtraction with other methods like wavelet denoising to reduce noise more effectively, leveraging strengths of different techniques. Then we have deep learning enhancements, which use your LLMs, your language models to estimate noise spectra and improve signal enhancements. DNNs also help in handling non-stationary noise. And then the statistical model, which adapt to different signals and noise types. Modern systems often combine classical and AI-based techniques to help boost these methods further. Now we have reached section 5, which is applications and performances. In the real world, spectral subtraction is seen in a wide variety of places, such as speech recognition systems. To improve speech accuracy, by cleaning speech signals before feature extraction. Then we have it used in telecommunications to improve call clarity in mobile phone and phone conferencing systems. And then also in hearing aids to enhance speech intelligibility for users, making the conversation more clean and comfortable for them. To evaluate performances, we have certain performance metrics, which are the signal to noise ratio, also known as SNR, which measures the ratio of desired signal power to noise power, which indicates better noise reduction the higher the SNR is. Then we have perceptual evaluation of speech quality, also known as PESQ, which measures perceived audio quality and quality of speech after processing, which gives us a subjective evaluation of audio quality. Then we have short-term objective intelligibility, which is STOI, which measures speech intelligibility as from the name itself, and also measures the correlation between clean and enhanced speech. These metrics help us quantify improvements after noise reduction. We also have the comparative analysis, which are performances with the different noise types, which evaluates spectral subtraction ability to reduce various forms of noise, such as white noise, Babel noise, real world ambient noises, and show performance capabilities. We have the comparisons to other techniques, such as Wiener filtering, Kalman filtering in terms of noise reduction, distortion, and computation efficiency. Now, we have reached towards the end and have reached the conclusions in the future directions. To conclude, spectral subtraction is simple and has get powerful in the frequency domain. We have few advantages, which are the spectral subtraction effectively reduces stationary noise and is easy for conceptual understanding, and it's a really powerful technique. Few of the limitations are that it's prone to induce musical noise and requires static noise to be effective. It is, and some other things are that it works really well, as told before, with stationary noise, which is also computationally efficient and forms the foundations for many enhancement techniques. Although it causes distortions due to formation of musical noise, its adaptive methods and multiband processing significantly improves performance. It's suitable for applications which need efficient noise reduction with limited computation power and processor, and does have very good processing power. Thank you for listening to. Sir, one second. We have a few more things. Sorry. Then we have future research areas. Non-stationary noise handling is one of the main areas, which is developing methods to dynamically adapt spectral subtraction to non-stationary noise environments for efficiency to improve performance. Then we have in the deep learning side, which uses deep learning models such as the LLMs to improve noise spectrum estimation and signal reconstruction to reduce distortions. Real-time optimizations. Optimizing algorithms for real-life performance on an embedded system and mobile device ensures timely noise reduction. I thank everybody for listening to my presentation today. Hope this presentation helped you understand spectral subtraction method clearly. Thank you very much.